Symmetric cryptography has many nice properties and a large variety of applications, but it has one major drawback. If you want to be able to use a potentially unsecure network today, then you must have had access to a secure network early on. That's because you have to exchange the key, and obviously you cannot exchange the symmetric key on an unsecure network. Now, to solve that, there are really two solutions. Number one is to come up with a secure key exchange algorithm, so the idea that you can establish a common key on a potentially unsecure network. And number two is usually referred to as public key or asymmetric cryptography, and it follows the idea that you have two keys, a public and a private key, and you're never going to share your private key. And that is exactly what we are going to look at right now. All right, now let's get started with asymmetric cryptography, or also public key crypto. Now, it's not entirely true, because the first example still is symmetric crypto. It just solves the key exchange, as you will see. But our second example, and also the examples in the next slide decks, will be asymmetric crypto. And this basically is the first foundation for you to understand what's going on. All right, so the first example, as I mentioned, of still a symmetric encryption, but something that solves the key exchange we talked about last time, so that allows you to exchange or establish a key on a non-secure channel, is based on a paper by diffie-hellmann-merkle, and they found this solution in 1976. As I mentioned, it is still symmetrically encrypted, so you will use the same key to encrypt and decrypt. But you can establish this key on a potentially compromised channel. So it doesn't matter if there's someone in between, if there's an eavesdropper in between who listens to the information you're exchanging in the process of establishing this key, they will not gain the information they need to actually establish the key themselves. So the public information is not sufficient to come up with the key that is shared between the two parties, and you will see why this is the case when we actually go into the math. Now, when we set it up, what needs to be defined ex ante between Alice and Bob, and these are the two parties, Alice and Bob, that want to share something. Let's call the potential eavesdropper Eve, the person in the middle. What they have to define ex ante is a one-way function, in this case g, which is a generator to the power of x mod p. And of course they also have to define the parameters g 7 and p 11. Now, there are certain requirements. We're not going to touch on that. For example, prime numbers, and also for the generator, the field where you have to pick it from. But in any case, we are going here with super simple examples. Because another requirement obviously would be that these numbers are sufficiently large, so you cannot brute force everything later on. Here's just a pen and paper example for you to easily follow what's going on. But once again, in order to be actually secure, these numbers need to be much larger, of course, and need to fulfill certain requirements. Now, when we look at it step by step, first of all, here on the left side, here in this column right here, you have everything that Alice does and sees. Here on the right side, you have everything that Bob does and sees. Now, we assume that everything that has been established so far, so the function and also the parameters, is known to both parties. And we also assume that a potential eavesdropper, so Eve in our case, could also have access to these variables, to these parameters that have been established in advance. Okay, so the first step is that Alice in private chooses A. That is her private information. She's not going to share this number with anyone whatsoever. So at no point in time this will be shared. At the same time, Bob chooses B, also a number he is not going to share with anyone. So this will never touch any unsecure channel, because there is no requirement to share this actual number. Okay. So this is private information to Alice. This is private information to Bob. And A is 3 and Bob is 6 in our case. So step 2. Alice will compute alpha, and alpha is just the generator to the power of A and everything mod p. And in our example, that's 7, that's the generator to the power of 3, which is A, the number she's chosen, mod 11, which is 11 is p, and 7 to the power of 3 mod 11. When you compute that as we did in the last lecture, you will end up with 2. Alice then takes this value and sends it this value alpha, and sends it to Bob. Okay, so this alpha value, this number 2, it will touch the unsecured channel, and therefore we assume it could be potentially known also to the eavesdropper Eve. Okay, but Alice, again, Alice is not going to share A, so the private information A remains hidden. It's only known to Alice. It's not going to touch the unsecured channel. On the other hand, we have Bob, and Bob computes a beta, which is the generator to the power of B, mod P. In our example, it's 7 to the power of 6 mod 11, which corresponds to 4. And he also shares this number beta with Alice, and beta equals 4 in our case. But once again, just to repeat things, then B, value B, so number 6 is not going to be shared with Alice. It's not going to touch the unsecured channel, so it will not be known to Eve. Okay. Now in step 4, Alice will compute K, and K can actually be computed by using beta, that's the number she received from Bob earlier, okay, and might be potentially public, to the power of A, that's her private information, that's definitely not public, it hasn't been shared with anyone, mod P. In our example, K would equal 4 to the power of 3 mod 11. That's when you just use the respective values for these parameters right here. That would be 64 mod 11, and that would be 9. Okay, so Alice would come up quite easily with the value 9. And Bob, on the other hand, Bob is going to use alpha to the power of B. Alpha, the value he received from Alice. Alice sent him the alpha value earlier. B, the number, his private number, so the one he has chosen initially and it hasn't shared with anyone. And everything mod P once again, so we have K equals 2 to the power of 6 mod 11, which is 64 mod 11, which is again 9. And as you can see, they both come up with the same number. They didn't have to share any information that would allow Eve, the eavesdropper, to come up with this number, because it's always a combination of some private information they kept to their own, and the information that was exchanged through the public channel. And obviously Eve doesn't have access to the private information. So the key, as I said, they end up with the same key, in this case 9, because alpha to the power of B mod P equals a generator to the power of AB mod P equals generator to the power of BA mod P equals beta to the power of A mod P. Okay, and as you can see, these are all various ways to come up with K. I mean that these are various alternatives to compute K, but none of these are accessible to an eavesdropper, because there's always some information in there that isn't publicly known, and that's the idea and the intuition why Eve will not be able to come up with this value. Once you've established this value, so the key 9 in this case, you can use that to encrypt the information. And as I've mentioned, even though it's a key exchange that allows you to use unsecured channels, the actual encryption is still symmetric, so you will use the same key for encryption and decryption. And that's the definition of symmetric encryption. That's the definition of symmetric cryptography. Now, that's great, and that's a big step up, especially for when you have to establish a key remotely, or these things then can be used on battlefields, for example, when you have to establish this key, or in communication also, for example, when you're a computer network and you don't happen to have a secure channel with the other person, and this is a great way of establishing a symmetric key that can later on be used to encrypt every subsequent message. So potentially speaking, you could do that with the handshake, with the initial connection. You could enter this key ceremony, this key establishment process, and then use the key later on to encrypt any subsequent messages, and prevent the eavesdropper from listening in and actually making sense of the data you're communicating. Now, there are certain drawbacks. First of all, there could be, I don't even have that on the slides, but there are certain attacks you can that could potentially work against this scheme. For example, what if you're actually communicating with someone you're not expecting to communicate? What if the eavesdropper actually responds to your messages? That's quite an issue in some cases, but more importantly, and that's where I'm going with this image right here, is the communication must be synchronous. So you have this process where you need to exchange some information in the beginning, where you have to respond to some of the things the other party does in a somewhat synchronous way. And this isn't always going to work. When you think of it, for example, that somebody is in the US and someone is in Switzerland, and you have to establish this key, and it might not be the easiest to actually respond to the message and just do that in a synchronous way. Of course, you could automate it, but then you'd still have the problem that you had a separate setup for each peer, which might be a big issue when you think of all of these economic agents, and that each and every one has to establish this key process with each and every one of the other agents. That would be really cumbersome and actually a waste of resources. So there are some drawbacks, even though it's a great step forward, and the following approach is about to solve many of these drawbacks. So far we have only talked about symmetric cryptography, symmetric encryption, where, as I've mentioned, decryption is the inverse of encryption, so you're using the exact same key. Diffie had an idea in 1975 that is asymmetric encryption, where you have one key to encrypt and the key to decrypt. They are related, so it's a set of keys, it's a pair of keys, but you can only decrypt something with the corresponding with the key that corresponds to the encryption key, but you cannot use the same one. Okay, so there's this mathematical relation between this pair of keys, where you have this public key and private key that can be used for decryption and encryption, and vice versa. But how are you going to do that exactly? How does it work? And the first practical solution, I mean, so far it's only been theoretical, the idea. It's been a great idea, but they couldn't find any mathematical equations, any functions that would actually satisfy the properties to establish something like that. And it has been done by Ronald Rivest, Adi Shamir, and Leonard Adleman. It was inspired by the idea of Diffie. And what they did is they published this paper, Method for Obtaining Digital Signatures in Public Key Crypto Systems, and came up with the algorithm that is today known as RSA. So Rivest, Shamir, and Adleman, RSA. And that's what we're going to look at right now in a more mathy sense. Before we do that, you've already seen this in an earlier lecture in the Bitcoin primer, so I'm not going to spend too much time on it, but just to give you some intuition, again, there are these two ways. So again, you have the public key, you have the private key. When you want to keep something secret, what you're doing is you're using the recipient's public key to encrypt the message, and then since the recipient is the only party in possession of the corresponding private key, they are the only party that can decrypt it, but you also can use it for integrity and authenticity. What you're doing then is you have the message, and you're basically encrypting the message with your own private key. Here it's not about secrecy, here it's just as a proof basically that you have been in possession of this private key, so that you are you and that this message corresponds with what you wanted to say. And then everyone else can use your public key to decrypt that message and actually arrive with it, and therefore validate whether this message has originated with you and whether it is still in an unchanged state. So that's the intuition behind it. We've talked about that already, so I'm not going to spend too much time on it. Now let's go into the math. What you do is, again, we go with the example of Alice and Bob. Alice chooses two primes, P and Q. So in our example, we go with P17 and Q equals 11. And then she computes N, which is just P times Q. So in our case, it would be 17 times 11, which is 187. And then she chooses an additional integer, which could be, which is referred to as E, and in our case is 7. Now what's really important is that this E value and the value P minus 1 times Q minus 1, that we will later on refer to as phi of N, must be relatively prime, so they cannot share any factors other than 1. Okay, that's just a condition that needs to be satisfied. Now n and e together make up the public key of Alice. I'm just going to make that publicly available so everyone will know her public key. It's these two numbers, so it's number n, which is 187, and number 7, and number e, which is 7. Okay, so step 2 is someone is going to encrypt a message using Alice's public key. So in this case, it is Bob, and first Bob encodes the message m as an integer. Encoding is not encrypting. Encoding is just representing it in some value. Here, for example, we have the letter X that needs to be represented in numbers, and in ASCII, I've shown earlier in ASCII, then converted to decimal, that would be 88. So we have letter X, which is represented by 88, and then we compute the encrypted message C using Alice's public key. Okay, so we take this message. The message is just the letter X. For simplicity, we're not going to use any complicated text or anything like that. We just say our message is X, and now we're going to compute the cipher C, so the encrypted message, and we're going to do that with M. So our message value, which is 88, to the power of E, which is to the power of 7, mod n, and you recall n in our example was 187, and when you compute that, 88 to the power of 7 mod 187, you end up with 11. That would be our cipher, our encrypted message. Step 3 is the derivation of the private key, and obviously that's something only Alice can do. If just anyone could derive the private key, that would be really bad. That would not be a good idea, because then everyone could decrypt the message. So it must be some restriction, some limitation in there that only Alice has access to this private key. Okay, and the way she does that is, that's somewhat complicated. She's going to compute K of P, that's the private key, and she's doing that by looking for a value Kp that times E. Okay, we know E is 7, will lead to 1 in mod phi of n, okay? Where phi of n, as I mentioned earlier, is p minus 1 times q minus 1. So we're looking for a value Kp that will result in 1 when we compute it as mod 160, okay? So 7 times Kp must equal 1 mod 160. And you can compute that in various ways. Usually people employ the extended Euclidean algorithm for that. I'm not going to touch that in this lecture, because we can, in this simple example, you can simply do it by trial and error. You will see when you add 23 in here, then it will be 161, and 161 mod 160 equals 1, the remainder is 1. But if you're interested in the extended Euclidean algorithm, there are great resources online, and you can do that on your own. Step number 4 is actually the decryption of the message, so decrypting it, and Alice can do that, can decrypt Bob's message. So we're looking for a function that yields M, that's the clear text, plain text message, and she can do so by taking the cipher C, the encrypted message, to the power of her private key, mod n. Everything is known to Alice, but note that the private key is not known to anyone else, so this will be a problem that's not solvable by anyone else if certain conditions are met, if the space is large enough, for example, if the numbers are large enough. But Alice can easily compute that. M equals 11 to the power of 23, mod 187, and in our case, this would be 88, which is X in ASCII. So basically what we started with, so we just gonna encode it and decode it from the number to the text again in ASCII to end up with the message, and the message was X, as you know. Good. Now there are a few requirements. Requirement number 1, n has to be sufficiently large. Obviously, these have been really easy examples, but when you want it to be secure, then obviously you have to use much larger numbers. In particular, it has to be impossible to find p and q by using prime factorization of n. So n is publicly known, p and q are not. And when you have really small numbers for p and q, and therefore for n it would potentially be possible to find out what p and q numbers lead to n, so to factor it, and that would be really bad. In this case, the RSA would not work. So you have to make sure that when you're actually using it in a context that is security critical, where you actually want to be sure that the information cannot be read by anyone else, you have to use numbers that are large enough. It's not going to work when you use these really small example values. But that being said, of course, examples are useful. Examples are great if we want to get an understanding, and that way you know what's going on, and you also know now that in practice, when you're actually applying it, you need larger numbers. All right, that's it. Again, 2 references. This is the original RSA paper that we've been talking about, and here once again the codebook. I've already talked about that several times, so I'm not going to do it again. That's it. Stay curious. See you soon.